Hello everyone, my name is Xuanting Lai, and this is the Soil Dynamic Final Report presentation. My topic is Multi-Platform Soil Structure Interaction Simulation of Dakai Subway Tunnel during the 1995 COVID. This is my content of my presentation today. First is the project description. It will talk about the spatial simulation called multi-platform soil structure interaction simulation, and then is the description and soil and numerical models and simulation results. That is my conclusion. So here we can see the flowchart of multi-platform soil structure interaction simulation. It is developed by the team from University of Toronto, called UTSIM. We can see it divides the model into two parts, the soil domain model and tunnel model. In soil domain model, first do the equivalent linear site response analysis in deep soil software. Next is check soil layer shear model and damping ratio equivalent to nonlinear soil. And last, we can establish the 2D plane strain soil domain model in OpenSys. For the tunnel, just establish 2D tunnel model and vector 2 according to the tunnel geometry and references details. Next is about the case description. The case that used to verification the model is the classical disaster happened in Japan. It was the Kobe earthquake, caused the Dakai subway station in a serious damage. About 30 central columns of the Dakai subway station to buckles and complete collapse. The surface after collapse underground looks like the picture on the left. You can see the ground almost settlement from the center of the road. Kobe earthquake happened in January 17, 1995. It is destroyed seriously in Kobe City, which magnitude 7.2 in JMA. The closest record of ground motion is 4.2 meters far from the Dakai Tunnel site in Port Island. The vertical area record the Kobe ground motions at 4 depths, 0, 16, 32, and 83 meters below the ground surface. The data as the depth of 83 meters is used in the numerical analysis shown as the picture below. And then this is the diagram of the tunnel from Dakai station. So here we talk about the numerical model. Before building the model, the soil parameters about building the numerical model is important. The soil condition is from borehole at southeastern portion of the Dakai tunnel site. After the earthquake shaking, tunnel is built in 4.8 meters under the surface. And here we can see the table that shows the detailed value of soil parameters on site. The soil on site is is sand and clay, and it was layer by layer. So after we checking the soil parameters, we can build a numerical model. First, can see the 2D soil models with the depth 30 meters and a width of 100 meters, which can ensure the free field boundary won't influence the soil-tunnel interaction. After the tunnel and soil models are established in Vector 2 and OpenSys, the model will be integrated, and the model that be integrated will be here. We can see that there are some interface between the OpenSys and Vector 2 models that are located along the tunnel perimeter. And then, in order to get the shear models and damping ratio at each depth, the other teams do the equivalent linear analysis. The result is shown in here. That's the effective shear strain ratio in the range of 0.5 to 0.2 does not largely impact the maximum shear strain profile. So they use the alpha equals to 0.2 to calculating the shear models and damping ratios of each soil layers. And then we come to the simulation results. The dynamic analysis is carried out under the horizontal and vertical ground motions simultaneously. The ground motion components are from Kobe earthquake records at Port Island. Vertical area at a depth of 83 meters. The result of peak deformation of soil and tunnel models scale up to 10 times, shows as on the right side in this page. The maximum horizontal displacement is 212.8 millimeters, and the maximum vertical displacement is 39.6 millimeters. As the figure can see, the structure and tunnel have lots of deformation. It was already failed. And then the failure of the center columns is happened as t equals to 5.6 seconds. As the center column experience a steady declination in the shear stress. Soon after reaching the peak value, the shear stress decreased 35% in actual load. And then the columns after 6.72 seconds it developed the permission actual displacement almost double the initial actual displacement. The center columns only supporting 25% of its initial actual load by the end of the dynamic analysis. So here we come to the last one, the conclusion. The failure of the center columns is inevitable at t.5.6 seconds. As the center columns experience a steady decline in shear strength, soon after reaching the peak value, the shear stress decreased 35% in actual load. As the result get from multiple platform simulation framework and compares to other that also analyze the dark tunnel collapses, we can prove that this analysis system can simulate the situation more really. I think this method can be linked all different kinds of group in civil engineering. If we makes the database, maybe we can decrease more and more disaster caused by earthquake. And thank you everyone for your attention. Thank you.